Okay, so remember this is where we left off in the previous lesson here, was that we had gotten VE to be VB1 plus VB2 over 2 plus R pi plus RB over beta plus 1 RO. Now, we need to now consider the output, V out, which is our output voltage. Now remember, we have one or two-sided outputs. So recall we have one or two-sided outputs. So what we're going to do is we're going to only consider at this point the one-sided output. And what we're going to do is we're going to consider that V out, the one-sided output voltage, is on the collector of the second transistor. So I'm going to scroll back a little bit here. So if we look at this here, we can see here, well, we have ground here and V out here. So the current is going this way. So we would simply have that V out would be equal to negative GM V pi 2, because that's the current, times RC. Okay, well, now let's go back to that circuit again here. V pi 2 is VB2 minus VE over the sum of those resistances. Well, it's not that. Let's get to the equation here. Let's recall. This is my equation I'm talking about right there. So what I'm going to do here is I'm going to lasso that equation for us. And I'm going to go down here. So this is where we're at. And I'm going to put this over here. So we have this from previously. And I'm going to do something I don't typically like to do, but I'm going to rewrite this then here, is that V pi 2 is VB2 minus VE over R pi plus RB times R pi. So if I plug that in now, I get that this is equal to minus, so I'm substituting this in here, just remember, in for there, minus GM R pi times VB2 minus VE over R pi plus RB times RC. Okay, but then we should recognize here that this, and I'm just going to erase it and rewrite it, that's just simply beta. So I'm going to rewrite this here as minus beta times that. Okay, so we're in a good progress here, but now we can see here this VE, which we said we were going to need that, that's right up here. Oh boy, is this going to get ugly, because what are we going to do? We're literally going to substitute this in for VE. So let's do that. And we're going to substitute in. And I'm going to skip the algebra steps. If we do that, the result is that we get that V out is equal to minus beta RC over R pi plus RB times VB2 times 1 plus R pi plus RB over 1 plus beta RO minus VB1. Because if you just even think about this here, we have this VB1 plus VB2, but we're doing VB2 minus VE. So VB2 minus VE, that's why we're going to get that minus VB1 there. And then this is all divided by 2 plus R pi plus RB over 1 plus beta RO. Oh, pretty ugly here. Now, if RO is infinity, or quote large, and that's what it'd be if we have a high VA, this equation reduces. Well, let's see what would happen here. I'm going to draw some green and then I'll erase it. Well, if this is big, that means this term is going to go to 0. This term would also go to 0. So you'd be left with VB2 minus VB1 over 2. So it actually simplifies down quite a bit. So I'm going to erase those lines just in case I need that equation again. We get that V out is equal to beta, well, negative RC VB2 minus VB1 over 2 R pi plus RB. Now, you might say, how do we ignore this here? Well, even because we're going to have RO again that we're going to consider again, but let's think about why we're just going to ignore RO in this step of the derivation of the equations we're looking for. Why would we ignore it? Because again, if RO is big, but then remember also here, beta is around 100. So even if RO was only 10 kiloohms, which, you know, that would be a really small value for RO. You'd have 10 kiloohms times 100, which would be 1 megaohm, and then RB and R pi we know are going to be in the kiloohm range at best, you know, the combination of them. So you'd have kiloohm divided by megaohm. Okay, that's essentially 0. Okay, so this is going to be a valid assumption no matter how big the RO is. So we don't even have to really necessarily assume it's infinity. We can just assume that it's, quote, large. Because, again, you know, maybe the early voltage, if worst case scenario, you could get a 10 kiloohm RO from your early voltage, which would, again, that would be really small. You'd have a pretty steep slope on those current curves. And so we would still, though, be able to ignore the term here. So we will, no matter what, regardless of whether we have to consider early voltages or not, we will always have this here. So we are not necessarily saying, oh, well, if we do have early voltages, we have to consider the other equation. No, we just consider this equation that I just boxed. Now, let's continue on with our discussion here. So we have, though, notice here, VB2 minus VB1, by definition, this is my differential voltage. So V out is then equal to minus beta RC VD over 2 pi R pi plus RB. So my differential voltage gain, which would be V out over VD, is minus beta RC over 2 R pi plus RB. Okay, so let's take a side note here and look at something here. If RB is equal to 0, AD is minus beta RC over 2 R pi, which is equal to minus GM RC over 2. This is the same as AD for DC. Because now remember, we're doing small signal here, and I'm going to scroll back here and find it. It'll take me a second to find it here. One-sided, two-sided, IREF here, V out, two-sided output. Right here. Here we go. One-sided output. And now remember, this was for DC analysis. This was not for AC. We had, and there should be actually a minus in there, but we had GM RC over 2. And now if we scroll down here for small signal, GM RC over 2. So we get the same thing for both the AC and DC for the differential gain, which is kind of interesting. All right. I think I'm going to go ahead and end the video here. We still need to talk about another type of gain here before we do an example, and also something called the common mode rejection ratio.